three-phase electrical systems, voltage and current measurements are typically provided in terms of line-to-line or phase-to-phase values. The actual voltage or current flowing in each phase is different from the line-to-line values. The relationship between line-to-line voltage and phase voltage is that phase voltage equals line-to-line voltage divided by the square root of 3. In a symmetrical three-phase system, the phases are 120 degrees apart. This means that the voltage or current in each phase reaches its peak at different times. Consider the following: the phase voltages are offset from each other by 120 degrees. At any given instant, the sum of the phase voltages is always 0. If we take the instantaneous values of the three-phase voltages and add them up, we get voltage AB plus voltage BC plus voltage CA equals 0. This is because at any given moment, one phase is at its positive peak, one is at its negative peak, and the third is at 0. However, if we take the root mean square values of the three-phase voltages and add them up, we get line voltage RMS plus line voltage RMS plus line voltage RMS equals the square root of 3 times the line-to-line voltage RMS. This is because the RMS value of a sine wave is related to its peak value by a factor of 1 divided by the square root of 2. Therefore, to convert from line-to-line voltage to phase voltage, we need to divide by the square root of 3. Similarly, phase current equals line current divided by the square root of 3, where phase current is the phase current and line current is the line current. In conclusion, the square root of 3 is used in three-phase calculations because it converts between line-to-line and phase values. This is necessary because the actual voltage or current flowing in each phase is different from the line-to-line values. Let's delve a bit deeper into the three-phase system and understand the root of 3 factor more comprehensively. Imagine a Y-connected system. In a Y configuration, the line voltage is the voltage measured between any two of the 3 lines coming from the source or going to the load. The phase voltage, on the other hand, is the voltage measured from one of those lines to the neutral point in the Y. The neutral point is the common connection point of the 3 phases. Now, to visualize what's going on with the voltages, we can use a phasor diagram. A phasor is a vector that represents a sinusoidal function, like voltage or current, and it has both magnitude and phase angle. In a balanced three-phase system, the three-phase voltages are equal in magnitude and are 120 degrees apart from each other. If you draw these 3 phasors, you'll see they form a symmetrical pattern. The line voltage can be found by taking the vector difference between 2 of the phase voltages. When you do the vector math using trigonometry and the law of cosines, you'll find that the magnitude of the line voltage is equal to the square root of 3 times the magnitude of the phase voltage. That's where the square root of 3 comes from mathematically. It arises from the geometric relationship between the phase voltages and the line voltages in a Y-connected system with a 120-degree phase separation. In a delta-connected system, things are a bit different. In a delta configuration, the phase voltage is equal to the line voltage. The voltage across each phase winding is the same as the voltage between any 2 lines. However, the line current is not equal to the phase current. The line current is the current flowing in each of the 3 lines, while the phase current is the current flowing through each of the delta-connected windings. Again, using a phasor diagram and vector math, you can show that the magnitude of the line current is equal to the square root of 3 times the magnitude of the phase current. This relationship is due to the way the currents from the 2 phases connected to a line combine vectorially. Each phase contributes a component to the line current, and because of the 120-degree phase separation, the line current ends up being larger than the phase current by a factor of the square root of 3. Understanding these relationships is crucial for several reasons. Firstly, it allows us to calculate voltage and current levels throughout a 3-phase system. If we know the line voltage, we can calculate the phase voltage and vice versa. This is important for selecting the correct equipment and ensuring that everything operates within its rated voltage and current limits. Secondly, it helps us calculate power in a 3-phase system. The total power in a balanced 3-phase system is equal to the square root of 3 times the line voltage times the line current times the power factor. The power factor is the cosine of the angle between the voltage and current, and it represents the fraction of the apparent power that is actually being used to do work. Thirdly, understanding the square root of 3 relationship is essential for troubleshooting three-phase systems. If we measure a line voltage that is significantly different from what we expect based on the phase voltage, it could indicate a problem with the system, such as an unbalanced load or a fault. In summary, the square root of 3 is a fundamental factor in three-phase electrical calculations. It arises from the geometric relationships between voltages and currents in Y and delta connected systems, and it's essential for calculating voltage, current, and power levels. Ignoring the square root of 3 factor can lead to incorrect calculations and potentially dangerous situations. It's important to remember that these relationships hold true for balanced three-phase systems. A balanced system is one in which the three-phase voltages are equal in magnitude and 120 degrees apart, and the loads on each phase are equal. In an unbalanced system, the voltages and currents are not equal, and the calculations become more complex. Firstly, understanding the vector relationships in three-phase systems is key to grasping the origin of the square root of 3. In a balanced three-phase system, the 3 voltage or current waveforms are 120 degrees apart. This phase difference is crucial. Secondly, in a Y-connected system, the line voltage is the vector sum of 2 phase voltages. Due to the 120-degree phase difference, this vector sum results in a line voltage that is √3 times the phase voltage. Thirdly, in a delta-connected system, the line current is the vector sum of 2 phase currents, leading to a similar relationship where the line current is √3 times the phase current. The formula that relates these is line voltage equals square root of 3 times phase voltage in a Y configuration, and line current equals square root of 3 times phase current in a delta configuration. Using the square root of 3 allows for accurate calculations of voltage, current, and power in three-phase systems. This is essential for designing and operating electrical systems safely and efficiently. Neglecting this factor can lead to incorrect sizing of equipment and potential overloads. The square root of 3 is important when calculating power in three-phase systems. The three-phase power equation includes the square root of 3 to account for the phase relationships. Remember that these relationships apply to balanced three-phase systems. In unbalanced systems, the calculations are more complex and require more advanced techniques. Understanding these concepts is crucial for electrical engineers, technicians, and anyone working with three-phase electrical systems. A solid grasp of the square root of 3 and its implications is essential for success. The relationship between line and phase quantities, whether it's voltage or current, depends on the type of connection, whether the load or source is Y or delta connected. Let's clarify the relationships in both configurations. In a Y or star-connected system, the line voltage, which is the voltage measured between any 2 lines, is equal to the square root of 3 times the phase voltage. The phase voltage is the voltage across each individual winding or impedance. However, the line current, which is the current flowing through the line, is equal to the phase current, which is the current flowing through each individual winding or impedance. Therefore, in a Y connection, voltage gets the square root of 3 factor. In a delta connection, the line voltage is equal to the phase voltage. The voltage between any 2 lines is the same as the voltage across each winding or impedance. However, the line current is equal to the square root of 3 times the phase current. The line current is the current flowing through the line, and the phase current is the current flowing through each individual winding or impedance. So in a delta connection, the current gets the square root of 3 factor. Consider a 480 volts three-phase system. If it is Y-connected, the line-to-line voltage is 480 volts. The phase voltage, the voltage from any line to neutral, is 480 volts divided by the square root of 3, which is approximately 277 volts. If the system is delta-connected, the line-to-line voltage is 480 volts and the phase voltage is also 480 volts. Now consider a system with a line current of 10 amps. If the system is Y-connected, the line current is 10 amps and the phase current is also 10 amps. If the system is delta-connected, the line current is 10 amps and the phase current is 10 amps divided by the square root of 3, which is approximately 5.77 amps. These relationships are critical for calculating power in three-phase systems. The total three-phase power is given by the formula power equals square root of 3 times line voltage times line current times power factor. The power factor accounts for the phase difference between the voltage and current and is typically between 0 and 1. Now, let's talk about why the square root of 3 comes up mathematically. It has to do with the geometric relationships between the voltage or current phasors in a balanced three-phase system. The three phases are 120 degrees apart, and when you add these phasors together vectorially to find the line voltage or current, you get the square root of 3 factor. These are vector additions, not scalar additions, and that's why you can't just add the magnitudes directly. You have to take into account the phase angles. When you analyze the vector diagrams, the square root of 3 emerges naturally from the trigonometric relationships. Firstly, in a balanced three-phase system, the voltages and currents are sinusoidal waveforms that are 120 degrees apart. This 120-degree phase difference is a fundamental characteristic of three-phase power. Secondly, when you represent these waveforms as phasors, which are vectors that have both magnitude and angle, you can visualize the relationships between the line and phase voltages and currents. Thirdly, in a Y connection, the line voltage is the vector sum of two phase voltages. The angle between these two phase voltages is 120 degrees. When you perform the vector addition using trigonometry, the result is that the magnitude of the line voltage is equal to square root of 3 times the magnitude of the phase voltage. Firstly, let's discuss single-phase versus three-phase power. Single-phase power is commonly used in residential applications, while three-phase power is typically used in commercial and industrial settings. Three-phase power is more efficient and can deliver more power for the same amount of current compared to single-phase power. Secondly, three-phase power provides a more constant and smooth power delivery compared to single-phase power, which fluctuates more over time. This is because the three phases are offset by 120 degrees, which helps to balance the power delivery. Thirdly, three-phase motors and generators are generally more efficient, smaller, and lighter compared to single-phase motors and generators of the same power rating. The total instantaneous power in a balanced three-phase system is constant, while it pulsates in a single-phase system. In three-phase power, you generally have reduced conductor size for the same power delivered compared to single-phase power. Three-phase systems are generally used for high-power applications, while single-phase systems are suitable for lower power needs. Firstly, the square root of 3 is approximately equal to 1.732. It's a mathematical constant that shows up frequently in electrical engineering calculations, especially those involving three-phase power systems. Secondly, the square root of 3 is an irrational number, meaning that it cannot be expressed as a simple fraction. Its decimal representation goes on forever without repeating. Thirdly, you can easily find the square root of 3 using a calculator, but it's helpful to remember the approximate value of 1.732 for quick estimations. Using the correct voltage for equipment ensures proper operation and prevents damage. Using the square root of 3 is critical for accurate power calculations. It is also important to maintain balanced loads on each phase to avoid voltage imbalances and equipment malfunctions. Three-phase systems are widely used in many industries including manufacturing, power generation and distribution, and transportation. Firstly, let's talk about power transformers. Power transformers are used to step up or step down voltage levels in three-phase power systems. They are essential for transmitting power over long distances and for providing the correct voltage levels for different types of equipment. Secondly, transformers can be connected in different configurations such as YY, Delta Delta, Y Delta, and Delta Y. The choice of connection depends on the specific application and the desired voltage and current relationships. Thirdly, transformers are rated in kilovolt amperes, which is a measure of the apparent power that they can handle. The kVA rating is related to both the voltage and current ratings of the transformer. Let's cover induction motors. Induction motors are widely used in industrial applications due to their robustness, reliability, and efficiency. These motors convert electrical energy into mechanical energy and are used to drive pumps, fans, compressors, and other types of equipment. Induction motors come in different designs, such as square cage and wound rotor, and are available in a wide range of power ratings and speeds. Maintaining proper voltage and current balance in a three-phase system ensures efficient and reliable operation of electrical equipment. Voltage imbalances can cause motors to overheat, reduce their efficiency, and shorten their lifespan. Current imbalances can lead to increased losses in the system and can also cause equipment to malfunction. Now let's talk about power distribution. Power distribution systems are used to deliver electrical power from the source to the loads. These systems include switchgear, circuit breakers, fuses, and other protective devices that are designed to protect the equipment and personnel from electrical faults. Power distribution systems can be designed for different voltage levels and can be configured in different ways depending on the specific application. It's essential to follow all applicable electrical codes and standards when designing, installing, and maintaining three-phase power systems. These codes and standards provide guidelines for safe and reliable operation and help to prevent electrical hazards. Regularly inspect and test electrical equipment to identify and address any potential problems before they cause a failure. This includes checking for loose connections, damaged insulation, and overheating components. Firstly, grounding is an important safety measure in three-phase power systems. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to trip protective devices and prevent electrical shock hazards. Secondly, there are different types of grounding systems such as solid grounding, resistance grounding, and impedance grounding. The choice of grounding system depends on the specific application and the desired level of protection. Thirdly, it's important to ensure that all electrical equipment is properly grounded and bonded to provide a safe and reliable electrical system. Understanding the relationships between voltage, current, and power is essential for designing and operating three-phase power systems. The square root of 3 is a key factor in these relationships and must be taken into account to ensure accurate calculations and proper system operation. Firstly, when working with electrical equipment, always follow safe work practices and wear appropriate personal protective equipment. This includes wearing safety glasses, gloves, and other protective gear as needed. Secondly, never work on live electrical circuits unless you are properly trained and authorized to do so. Always de-energize and lock out the circuit before working on it. Thirdly, if you are not qualified to work on electrical equipment, always call a qualified electrician to perform the work. Power factor correction improves the efficiency of three-phase power systems by reducing the amount of reactive power that flows through the system. This can help to lower energy costs, improve voltage regulation, and increase the capacity of the system. Power factor correction can be achieved by installing capacitors or other power factor correction equipment at the load or at the source. Monitoring voltage, current, and power levels in a three-phase system can help to identify potential problems and prevent equipment failures. This can be done using meters, sensors, and other monitoring devices that provide real-time data on the system's performance. This data can be used to optimize system operation, improve energy efficiency, and prevent costly downtime. Remember that a solid understanding of the square root of 3 and its applications is crucial for anyone working with three-phase power systems. This knowledge is essential for designing, installing, operating, and maintaining these systems safely and efficiently.